Welcome to Randomized Algorithms. I successfully already lost my pen. That's not what here it is. So this is okay. So this week we are lecturing online because, well, I have to. And my assumption is that it's quite probable that also next week will be online. We will see. After that, we will move to hopefully physical lecturing, and we will do everything in class like the good old days. If you're here, I assume you got my email with all the information. I'm trying this platform called Ed or EdSTEM. I don't even know what the real name is, instead of Piazza, because Piazza have advertisement nowadays. We will see how well it works. On the web page, there are class notes from previous 2 semesters. I would try to post the class notes relevant for every lectures after the lecture or before the lecture. We'll see. It will take me a while to get my act together. There would be homework in the course. There are currently 42 students in the class, which is a bit too large to do things like projects. So we will see what happens by the middle of the semester. If the number of students will be much smaller, we will do some project in the end, because last time I did it, and I think both me and the students like it quite a bit. In any case, with this number of students, I'm going to have a final exam. And I might also have a midterm if there is demand for it. The final definitely would be multiple choice. As for homeworks, the homework would be in groups. The groups would be at least of size 3. I didn't decide yet on the upper bound, but the lower bound is 3. So you cannot submit on your own because, life is too short, and I have to do the grading. The number of homeworks will not be probably too large. I assume there will be 7 or 8 homeworks during the semester at most. Since it is a graduate class, the homework will be challenging. So you should expect this. Let's see if I can see the chat. You should be able to see the chat. And actually, if you have questions, you can ask them on the chat. I will try to check during the lecture. Now, a little bit on this. I'm yet to post office hours and stuff like that. It will take me a few days. Because until yesterday, I was in a state of denial about the beginning of the semester. Okay, what else? I don't think there's much more to add. I assume that you are taking the class because you are interested, right? So, and the homeworks, as I said, since this is a graduate class, the homeworks are going to be, some of the questions on the homework would be quite challenging. When I mean quite challenging, it's, there might be questions where I don't know the answer, right? Now, that doesn't mean that there is no answer. Usually, there might be questions that would be kind of open-ended, where I would just ask you to do as well as you can. And, I would have some kind of a baseline, what I expect, and would expect you to be able to do that or better. And hopefully those kind of questions tends to be more fun, but they tend to be much harder, right? So this is not an undergrad class where you see a homework problem and you just, even if you don't know how to solve it, it's kind of obvious what has to be done, right? Here, sometimes you would have to sit down and think for a while. So that's it. As far as final grades, it's an advanced, it's a 500 level class. Grade should not matter, right? So in a perfect world, the curve would be, large fraction of the class would get A, another large fraction would get A minus, and so on, right? Et cetera, a failing student in this class is kind of hopefully, I don't think it ever happened. Let's put it this way. Okay. So, are there any questions before I jump into telling you what are randomized algorithms? Okay.
One quick question. So when you say projects, what is this, like a survey, or what are you referring?
Well, since there are too many students in the class, let's revisit the question in the middle of the semester. Let's see if there are fewer students. But usually it's, at least last time, what I did was that I had a list of papers and I expected each student to read a paper and present it. Surveys tends to be less interesting, but yeah. And I should say that you can look on the previous semester to kind of see the list of topics I'm covering. I don't use a textbook. I have extensive class notes, which by now are enough to cover, I think, 2 semesters of this class. So it's much more about pick and choose what I want to cover. And every semester that I teach a class, especially a class like that, I try to teach at least one topic that I never done before, so that I learned something new. And I would definitely try to do it this time around. Yeah. Other questions?
Just one more thing. So what's the tentative distribution between homeworks and, like, anything you have in mind? Or?
The majority of the grade would be assigned to the exam, of course. Right. So the homework would be, let's say, 30 or 40%. Right. But the final would be the main thing, right? The homework policy is very flexible about essentially allowing you to collaborate and so on. So it's really intended for you to motivate you to learn the material and play around with it. It's much more, I give you some points for it, but the grade is not the main motivation, at least from my point of view. And, yeah. And as I said, the homework policy is similar to 374, 473 if you took those classes. You can work in groups, you can use any resource available in the internet or the universe, etc., etc. Yeah. Other questions?
Is there any samples for previous exam? I just want to know, like, what's form?
So there are links. Well, the exam would be different than previous exams. I don't think I did the multiple choice final in this course in the past. So that would be much more similar to my final exam in 473. So just think about an exam where you get a large number of multiple choice questions. Right.
Okay, sure. Thank you.
If you ask on the forum, I would be happy to send you a link to the, 473 exams. So, to just get the format, right? I can also look on previous semester. If the number of students was much smaller, like 10 then or 15, then I usually give take-home exam where, you're just given a week and you just do whatever you can, and that's it. And of course, but with 40 students, it doesn't scale up. So both the format of the final exam is kind of depends on how many students there will be in the class in the end of the semester. Okay, other questions? Okay, so let's let the lecture begin. Okay, so of course the question is, what are randomized algorithms? So randomized algorithms are algorithms that are allowed to make random decisions. So what do I mean by random decisions? You're allowed to, oh, by the way, that question in the, okay, there is a question on the chat whether we're going to cover complexity classes. Yes, we're going to cover a little bit of it, not too much. You kind of, when you do randomized algorithm, you need to essentially discuss the topic, but it's kind of a zoo. And there are some interesting results, but they tend to be more advanced. So I might do one of those advanced results towards the end of the class if we have the time and energy. Okay, so randomized decisions, right? So the way to think about it, that the algorithm is allowed to roll a dice to decide whether how to do something, etc. And of course, you might be familiar with quicksort as a good example, but let's maybe describe it instead of an algorithm. Let me give you an example of a game. Right. So the game is that we have a triangle with 3 vertices, and each vertex there is a coin. And the coin is either heads or tails. Okay, so there are 3 coins on the 3 vertices, and they're either heads or tails, each one of them. Now, unfortunately, the player, I'm going to draw you an amazing drawing of a player. They're going to have fingers. At least in one hand, the right number of fingers. Not on the other hand. They don't need 2 hands. Unfortunately, the player doesn't see the board. This is the board. Okay. And so this is a screen. The player cannot see through the screen. Now, the name of the game is that the player can ask let's call it an adversary. So the adversary runs the game, right? So the player can ask the adversary to flip a coin. In fact, the player can ask the adversary to flip 2 coins. And how do they tell them which coin to flip? They just tell them flip coin 1 and 2, for example. Right. Now, why are they doing it? Well, the game ends when all the coins are heads, let's say. So the board looks like that, or all the coins are tails. So if all the coins face all up or face all down, then the game is over, right? But so that, of course, is not a very interesting game, right? Because the player can just say, oh, flip 1, the player can essentially kind of enumerate all possibilities. So to make the game more interesting, the adversary, every time the players play, the players say, flip this coin, or play, as I said, you can also say flip 2 coins, doesn't really matter. The adversary is allowed to take the board. So let's assume this is an equilateral triangle. And the adversary can rotate it, right? So it can rotate it either by 120 degrees in this direction or 120 degrees in this direction. Right. So just think about the labels that I have here on the position 1, 2, 3, as that if I rotate by 120 degrees, I rotate the labels, right? So the adversary can rotate either clockwise or counterclockwise, or in fact leave the board as it is, right? Okay, so how is the game goes? Let's start from the beginning. In every round, the adversary rotate the board or keep it as it is. It's up to the adversary, and relabel the vertices according to the rotation. And then the player tells it which coin to flip or which 2 coins to flip. If all the coins are the same, the game ends and the player wins. If, on the other hand, the coins are not all the same, the games go on to the next iteration. Right? Okay, so let's think about what would be a natural randomized algorithm here, by the way. Anybody want to suggest something? You could suggest it in the chat if you don't want to speak up. Well, to begin with, I hope that the game is clear. Right, okay, so the most natural algorithm, randomized algorithm here, pick a random coin and flip it, right? Pick a random number between 1, 2, and 3 and flip it, and let's see why it works, right? So if you have 3 coins, right? So just think about it as 3 bits, right? Heads is 0, tails is 1. So essentially we have 0, 1, 1 or 0, 0, 1, right? You know, and all the permutation possible of it, right? Right. So the board might be in one of those 6 possibilities. So the important observation is that in any configuration of the coins, there are 2 coins that are the same, and there is 1 coin that is different, right? So the player is going to play a random strategy. It's going to randomly pick a number between 1, 2, and 3. It has a probability of third to pick the right coin to flip, such that all the coins become the same, right? So the probability of a third to succeed, the probability 2/3 to fail. If you fail, you repeat again, right? So this is kind of the basic, most basic randomized algorithm. We encounter it all the time. You're trying to do something. If you're successful, you're done. If you're not successful, you try again, right? Like in life. And you repeat until you succeed. Okay. Now, the probability of success here is a third. And now you ask, how many coin flip do I have to do to succeed? So this is known as geometric variable.
Professor.
Yeah.
Sorry to interrupt. I think sometimes when you're writing, it's really hard to hear. The microphone doesn't pick up your voice as well. I'm not sure
Okay.
I'll have the same.
Let's see if I can at least direct it in the right direction. I'm not promising
Thank
that
you so
will
much.
be a huge improvement. Okay. I can try and I don't know. I'm not sure that would be better. Okay. Let's. Okay, I don't think. Well. Okay, is it better now? Can you hear me at least?
Oh, yeah.
Okay.
Thank you so much.
Yeah, we will see later on. Okay. So this is geometric variable with probability third to succeed. So what is the expected number of coin flip till we get till we succeed? How many rounds do we play in expectation? Just, yeah, 3, right? So in expectation, we expect to play three rounds. Notice that we might be extremely unlucky, right? We might be extremely unlucky, and every guess we make is wrong, right? And then we play and play and play and play and play, and nothing good would happen. But the probability for that is extremely small. Why is it small? Well, the probability to fail that in a round is 1 minus 1 over third, right? Probability of success is a third. Probability of failing is 1 minus this. So the probability that they fail for I iteration is this, 1 minus third to the I. And now I'm going to use one of these inequality that, again, we are going to use all the time in this course, which is that y minus x is smaller than exp of minus x. Okay, this is definitely true for any x in 0, 1. In fact, it's true for any x. So this is smaller than exp of minus third to the I. This is, of course, no more than exp of minus I over 3, which, of course, is, as I becomes very large. Okay, why did I complicate this? Okay, it doesn't matter. Because we're going to use this argument again. We don't need to really complicate it. Anyway, this is 1 over e to the I over 3. If I is very large, this probability is extremely small, right? So we are in this bizarre situation where the game might continue forever, but the probability for that is essentially 0, right? In fact, we expect to terminate in 3 steps, okay? So this already shows you that things are going to be more complicated than deterministic situation, because every time we run the algorithm, we might get a different running time. And when we speak about randomized algorithm, we'll be interested in how is this running time behaves. What's the expected running time? Maybe bound the running time with high probability. Some randomized algorithm might fail, right? We'll see an example of that shortly, maybe. So there are all those subtleties that we'll discuss later on. Now, this game is kind of interesting because there is no deterministic strategy. So any deterministic strategy fails in this case, which is extremely surprising. So if the player has a published strategy and he doesn't use any randomization, the adversary can always, in every step, predict what the player is going to do, rotate the board, and leave to play another round. Right? So there is no deterministic strategy, which kind of gives you the power of randomization. Right? The power of randomization here is that the player is unpredictable for the adversary, and that gives the player a lot of power, which otherwise it would not have. And that's really what's going on when we speak about randomized algorithms. Deterministic algorithms, I give you the algorithm, I give you the input, you know exactly what's going to happen. It's an execution pre-told, right? You just know what's going to happen. But when you have randomized algorithms, everything can happen, right? The algorithm might do bizarre things, right? Because it's allowed to flip a coin. And it can make some bizarre decisions, right? Hopefully, maybe later on in the course, we'll see things like rejection sampling, where the algorithm just rejects some stuff randomly. Why? Well, it turns out to work well. And that's important. Why is it important? It's important because the way we usually think about algorithms, we really think about when we analyze algorithm, we think about algorithms as a game. We do worst case analysis. Right. So what is worst case analysis? We have a problem. Somebody come up with an algorithm, right? And then the way we analyze it, we say, okay, there is an adversary. The adversary has infinite computation power, infinite time. They look at the algorithm and they come up with the worst possible output, right? And we run the algorithm on the worst output, and whatever running time we get, this is the bound of the running time of the algorithm, right? And this is unbalanced, right? This is kind of unfair, right? Because the adversary have these unbounded resources to figure out what is the worst input, right? Randomized algorithm take back some of the power. It makes the adversary weaker. It can no longer figure out in advance what the algorithm does. And that turns out to be very important because a lot of algorithms, if you look at them carefully, especially more complicated algorithms that you might encounter, a lot of the analysis and the design of the algorithm is spent in handling what can be best described as boundary cases, right? Cases that might happen in practice. They're not like unthinkable, but they're not like the typical input you expect. And you spend a huge amount of energy on handling those special cases efficiently, right? Because of those worst case analysis, right? But the randomized algorithm the algorithm tends to be much simpler because they don't have to worry so much on the worst case. On the other hand, so a randomized algorithm tend to be simpler, by the way. What gets more complicated is the analysis, because now you have to predict what's going on and understand the behavior of this, if you want, kind of a randomized game. So that's why, at some level, why randomized algorithms are interesting. They are taking back some of the power from the adversary. By the way, before I move on, let me mention for this coin game, let me mention that if you play this with a square, so now you have 4 coins, okay? And the same game, except that you're allowing rotation by 90 degrees, 0 degrees, of course, no rotation, 180 and 270, right? So the adversary can rotate the board of size 4. And it turns out for this case, there is a deterministic strategy, okay? So it turns out there is a strategy. I don't remember the number of steps, but there is maybe 7, let's say, or 10, something like that. There is a sequence of 10 steps, let's say 10, it's less than 10. There's a sequence of steps that the player takes that, independent of what the adversary does, the player wins. And of course, people now there's a complete characterization of which size of boards are winnable, deterministic, and which one requires randomization. The case of the 4 coins, deterministic strategy, it's one of those brain teaser problems. You can think about it. It's a fun problem. It takes maybe 15 minutes. It took me maybe 15 minutes to solve. So it's a fun problem to think about. Not related to the course. Okay, let's look on the time and let's see what I want to say next. Other questions before I go any further?
So one quick question. So just to confirm my understanding, in the game, the player was allowed to flip 2 coins, right? And in any number of coins on the board, there are always 2 coins he flips.
So the general version, you have an n-gon, right? The triangle is an n-gon, right? So think about the 6 gon. and the player is allowed to ask to flip any number of coins it wants. They're all labeled by, let's say, 1 to n, right? And the adversary is allowed to rotate the board, if there are n vertices by any angle that keeps the symmetry, essentially, right? But for the triangle case, flipping 2 coins or flipping 1 coin is the same thing. So, in fact, in the triangle case, only 1 coin is needed. And in fact, the randomized strategy works for any board size when you allow it to flip only 1 coin. But that's a side comment.
I think I missed this part. Pretty key part. What's the end goal of the game? Getting two
The
of
end
the
goal
same
of the
coin?
game is that all the coins would be either facing up or all heads or all tails.
Okay.
But
Got
the
it.
hardness here is the player does not see the board. It's one of those games that sounds a priori completely ridiculous, right? Play a game, but you don't see anything, right? Well, it's a Russian roulette with coins without the dying, which is good.
Can the adversary see the board?
Yeah. The
Okay,
adversary can see the board. The adversary, if the player not only the adversary can see the board, the adversary even know what the player's strategy is. But if the player's strategy is randomized, the adversary don't know the random decisions that the player make. Okay.
Is there any feedback other than the fact that
No, all the player is being told after every round is whether the game is over or not.
Wow. Okay.
Yeah, it's a fun game. Well, not if you're the player, but conception.
On the starting configuration, the adversary decides, right?
Yeah. You don't know the starting configuration, right? Not that it matters, but you don't know the starting configuration. Well, it matters, but the way I describe it, every round starts by the adversary rotating the board, right? So even if you know the starting configuration, once the adversary rotates it, you don't know it. So think about it, it's fun. Other questions? Okay, so let's maybe quickly go through. So what are the advantages of randomized algorithms? So for many problems, the best algorithm we have are randomized. Like in this game example, right? There is no deterministic algorithm, only randomized. Randomized algorithm tends to be faster in practice. Think about quicksort, much faster than any other sorting algorithm. As I said, randomized algorithm tends to be simpler. And in fact, there are a lot of problems where the only deterministic algorithm we know for a problem is by taking the randomized algorithm and de-randomizing it. De-randomizing randomized algorithm is that you essentially somehow remove the randomized decision of the algorithms. We will speak about it later on in the course. It's a very interesting technique. Well, it's a family of technique. And the rest, I think I mentioned already about adversarial behavior. Okay, one thing we are not going to talk about in this course is average case analysis. So average case analysis, another approach is to say, okay, if the worst case analysis is bad, right? Because I don't remember the name of the game. I would have to Google for it. A question on the chat. But there are papers on it. There is at least one paper on it. If you find it, just post it to the chat or the forum. Okay. So if worst case analysis is bad, one natural thing to do is to try and kind of look on real world inputs. The problem with real world input is it's very hard to get real world inputs. It's very hard to characterize them. it's very hard to say, no, this input is not a real world input. So one thing that people do, sometimes they think about the input that's being generated randomly. And there is a whole field of doing analysis for these cases. And this analysis tends to be, it gives you something, but it's not as interesting, right? Essentially, it says, if the input is generated randomly, you get an algorithm that runs in this time. We will encounter a few examples of this in the course, but this is not the main push of this course, and arguably it's less interesting. But it's important to know about it.
I'm sorry, I couldn't hear you when you said if the input is random, then what's the good strategy?
If the input is random, then you can try and analyze the algorithm for a random input. Think about a deterministic algorithm. For example, think about sorting random numbers. Right? I give you n numbers, but I pick them randomly at uniform. Right? So, for example, I pick n numbers at random. Sorry, the microphone moved. That's why you couldn't hear me. You pick n numbers uniformly at random from 0, 1, and now you want to sort them, right? So it's not hard to see, you can think about it too, it's not hard to come up with an algorithm that in expectation would take linear time to sort n such numbers. Although, of course, sorting n numbers in general takes n log n time, right? So somehow, the fact that I tell you that those numbers are picked uniformly at random from the interval 0, 1 really help you with handling the input. So we are not going to do much of this random, deterministic algorithm with random input and then analyze the algorithm. But I'm just mentioning that it exists. It's something that people do, but I find it less interesting. Okay. Other questions? Okay, so I want to mention some example of simple algorithms. Some of those algorithms are very simple. I'm not going to analyze them here because at least some of them, analyzing them is in fact surprisingly difficult and requires quite a bit of math. We will hopefully do them later on in the lecture, in the class. So the first one is 2SAT. So 2SAT is, I give you a formula that looks like the following. You have variables, let's say x1, x2 to xn. And you have clauses, right? The formula is essentially a clause, let's say x1 or x2 and x7 or x16 not, and so on, right? So it's a 2SAT is a 2CNF formula, so it's a conjunction, it's an add of clauses. Every clause is made out of two literals. A literal is a variable or its negation, right? And the problem, and let's assume this is of length m. There are m clauses, and n is the number of variables. Okay. And the question is compute a satisfying assignment. So what do I mean by a satisfying assignment? I mean, assign the variable values such that the formula evaluates to 1, to true. So this problem turns out there is a linear time algorithm for it, a deterministic algorithm. It boils down, after clever reduction, it boils down to computing strong connected components in the graph. Okay, so it can be done in linear time, but the algorithm is kind of clever. I want to describe to you a very simple algorithm. So what would the algorithm do? So the algorithm would do the following. It would start with an arbitrary assignment, right? So we, for example, we could just think about setting all the variables to 0. Okay. And now we have the formula. We evaluate the formula on the current assignment. If the formula evaluates to true, we are done. Otherwise, it fails, right? If it fails, it implies that there must be a clause somewhere which evaluates to false, right? So there is a clause where both literals are evaluating to 0. So here's what we're going to do. We're going to take this clause that failed. There might be a lot of clauses that fail, of course. And we are going to randomly choose one of the literals with probability half, either the left literal or the right literal. And then we're going to flip the value of the variable. So let's assume that we chose this variable, xi. We are going to flip the value of xi. Okay. So again, find a failed clause, randomly choose one of the two literal, and flip the variable that corresponds to this literal. Essentially, what you're doing, you're fixing this clause. Now, with this new assignment, this clause would evaluate to true. Okay, and we repeat this game until we find a successful assignment. Okay. Now, so the surprising thing, let me state it as a theorem, in expectation. So this algorithm is, of course, much simpler than the strong connected component algorithm. In expectation, the randomized algorithm let's say executes. So after quadratic number of iterations, the number of variables, the algorithm finds a satisfying assignment, which is kind of very surprising. Now, to remind you, people, of course, are very interested in the 3-sat version, where in 3-sat you have a clause with 3 variables, xi or xj or xk. Right? And 3-sat, of course, is NP complete or NP hard, depending on how you exactly state it. And you can kind of think why the randomized algorithm fails here, right? The randomized algorithm fails here because what does the randomized algorithm do? It finds a failed clause, right? It finds a failed clause which has 2 variables, x or y, let's say. And then it randomly chooses one of them. It chooses one of them and flip the value. Now, with probability half, okay, so what are the possibilities? It might be that in the current assignment, x and y are both assigned the wrong value. What do I mean by wrong value? They are not assigned the value assigned to them in the satisfying assignment, right? So if both of them are wrong, then it doesn't matter which one I choose to flip. When I flip it, I made progress. What do I mean by progress? I'm closer, if you look at the number of variables that have the same value as the satisfying assignment, the number of variables with the same value is larger, right? I got closer to the correct assignment. So with probability, if they're both wrong, assigned the wrong value, then I'm always making progress. The more interesting case is where one of them is assigned the right value and one of them is assigned the wrong value, right? One of them agrees with the optimal assignment, one of them disagrees with the optimal assignment. And then probability half, I might have guessed correctly and flipped the right variable, so that both variables now agree with optimal assignment. On the other hand, it might be that I failed, and in fact, I took the wrong variable, and the one that agreed with the optimal assignment, and I flipped it. So now there are less variables that agree with the optimal assignment, but the probability for that is half, right? So one can think about what's really going on here. What's really going on here is that we have this, let's say, call it OI would be number of variables in the assignment. The assignment at time I, which then agrees the satisfying assignment. Okay, so let's think about it for a second. If OI is equal to n, we are done, right? I'm assuming here that there is always a satisfying assignment. So if we reach a case where OI is equal to n, all the variables have the same assignment as a satisfying assignment, and I'm done. I found the satisfying assignment. Okay. Otherwise, what happened is look on OI and OI plus 1. Right? In every step, they differ by at most 1, right? Because I'm flipping the value of one variable. It either increased by 1 or decreased by 1, right? In fact, it equals to 1 because it never can be 0. So intuitively, what's happening is that let's think about this as we have the initial assignment, O0, or right, maybe O was not a great choice, but whatever. And then we start walking, right? In every step, the value change, and our purpose is to arrive to the value n. Right? Now, in every step, there are two possibilities. Either we go right, if both variables in the clause that failed are not assigned the right value, with probability 1, we are going to increase the value by 1 because we are flipping one variable to its correct value. That's one possibility. The other possibility is that with probability half, we go left, we decrease the value of number of variables assigned the right value by 1. Probability half, we go right. We increase the number of assigned variable by 1, right? So this process is called the random walk. I will describe it hopefully more clearly shortly. But for example, for the time being, just think about the random walk. And we have a starting value somewhere between 0 and n. And the question is essentially how many steps do you have to do until with good probability or the expectation you reach n. And it turns out to be n squared. So that's kind of very cool. The algorithm is pretty simple. This algorithm doesn't work for trisat, at least not in polynomial time. Well, if it did, then p would be equal to np. But the reason why it's not true is because we no longer have this equal probability, right? Essentially, you have 3 clauses, x or y or z, right? And essentially, there is a probability of 2/3 to go left, and only probability of 1/3 to go right, intuitively, right? Because there is the probability that you choose, maybe all 3 variables are assigned the wrong value. The probability you choose the right variable to change is 1/3, right? And now getting from whatever value here to get to n must be much harder, right? It's like walking against the wind, essentially. While in the 2-sat case, there's equal probability of going right and left. And it still turns out that this randomized algorithm for 3 sets still leads to a better algorithm. So you still get exponential time, but the constant is better than other algorithms. So it's kind of cool. Okay. Let me see what the question was in the chat and continue from there. If I can find the chats. Chat, where are you? Oh, okay, there wasn't a question in the chat. My bad. Okay. So let me speak a little bit about random walks because it's a really fun topic. So this is going to be, a lot of this course is going to be about just doing math because for randomized algorithm, you really need to understand the underlying math of the probability spaces and the random process going on and analyzing it. So, and some of this math is pretty surprising and pretty interesting. So let me zoom in. So let's speak a little bit about the random walk stuff. Okay, so imagine that you have the integers and you start at 0. And now, in every step, you either go left or you go right, one step, increase by 1 or decrease by 1 with probability half, right? And you start playing this game for a very long time. In fact, think about playing the game forever, okay? So the question is, if you play this game forever, how many times would you visit the origin? Oops. Anybody has any guess? Yes, no?
I think any random walk has a vanishing probability of never returning to the origin. So it was.
Yeah, so this is not quite enough because I'm asking how many times.
If you keep.
Yeah, but you're on the right track. So let me maybe say something about the maths. So if I start in the origin, at time 2n, first I can be in the origin only in even times, right? Because at odd times I mean at odd integers, in the even time I need the odd position. And now I'm going to be back in the origin only if I went, the number of times I went right is equal to the number of times I went left, right? So the probability for that in 2n steps, the probability for that is 2n choose n, right? This is the number of ways to choose out of 2n decisions. There's the number of times to choose exactly the same number of lefts and rights. Of course, divided by 2 to the n, which is the total number of choices. Okay. Now, sorry about shouting. Now you need to know a little bit of math. So let me just dump it for now. This is equal to roughly up to constant, essentially. So theta of 1 over square root n. I'm sorry. Let me be more precise. It's 2 to the n over square root n. Okay. You can see it from Stirling formula, but in fact, one can prove it with elementary mathematics. You don't need Stirling formula. Okay, so this implies that the probability to be at the origin at times n is something like 1 over, is roughly, because I don't care about constant, is roughly 1 over square root n. Okay? And now I'm going to do some fishy math. But intuitively, this is going to be the probability that I'm going to be in the origin in time to n. So the number of times I'm going to be in the origin is going to be right. This is the probability of me being in the origin at time 2n, and I'm just going to add it up. And essentially, this is the expected number of time I'm going to be in the origin, right? Why this calculation is true, don't worry at this time, right? But so this is essentially up to constant, and going to 1 to infinity of 1 over square root n. And of course, what is the summation of this? This summation diverge. So this is kind of interesting, right? The probability you're going to be in the origin at any point in time decreases over time, but in expectation, you're going to visit the origin an infinite number of times, which is kind of cool. Okay, can we do something more interesting? So in general, you can speak about random walks on graph, and people do that. There is a lot of interesting algorithms about random walks in graph, but you can also analyze random walks on special graphs. So for example, you can do random walk on a 2-dimensional grid. Again, you start from the origin, and now in every point in time, you decide whether to go to one of your 4 neighbors with probability quarter. Okay. And again, the question is, you can ask the same question: how many times would you visit the origin in expectation, or would you visit the origin only constant number of times if you start from the origin in this infinite walk? What is going to happen? Now, it turns out that, I'm not going to do the calculation now, but it turns out that the probability of being in the origin at times n, 2n, in this case, is roughly 1 over n. So the expected number of time you're going to be in the origin is going to be this, and this summation still diverges. So if you walk in the origin on the integer grid, you're still going to visit the origin an infinite number of times. Now, the interesting thing is that if you look on the 3-dimensional grid, right, so you have 3 coordinates and you have 6 choices, random choices, it turns out that in expectation, you visit the origin only a constant number of times, which is very surprising, right? So this is kind of one of the results I hope to show later in the course, which I find kind of interesting. Okay, let's see other examples. Oh, and I mentioned this walk on the grid and so on, because walking on the line is related to these 2 sat. You can essentially interpret the 2 sat as walking on the line, and once you understand the walking on the line process, you can understand the 2 sat algorithm. Okay, let me speak a little bit about RSA and primality testing. Maybe change the color. RSA and primality testing. So RSA is this public encryption system that's being very widely used. It is believed to be very strong. That is what SSH uses and a lot of other protocols on the internet. But we don't know it. What do I mean by don't know it? We don't know whether it's breakable or not. We believe it isn't, but it might be breakable. In particular, the main reason people are interested in quantum computing is because quantum computers can break RSA. And I'm not going to describe RSA in too much detail because it's kind of tedious, but the basic idea is that you find two random big prime numbers. Compute two large prime numbers. I'm oversimplifying things, by the way, just tell you in advance. And you can think about the P and Q as being your secret keys. And then you publish the product. This is the public key. Okay. And now the basic idea is that it's pretty easy to find prime numbers. I'm going to speak about it shortly, random prime numbers. So computing computing thousands of prime numbers is very easy. So computing n is very easy. But what we don't know how to do efficiently is factoring. Right? So if I give you n, and I tell you n is a product of two primes, computing those two primes, we don't know how to do efficiently. Here we're speaking about two prime now, n is something like 4,000 digits. Right, that will be a very strong RSA key. Right, so thousands of digits, and you need to find the two primes that are the product. So factoring, we don't know how to do it efficiently. Strangely enough, we don't even know if it's NP complete. So factoring is definitely in NP, right? If I give you n, you can guess P and Q, and you can multiply them and verify that indeed n is equal to PQ. But we don't know, it's open whether the problem is NP hard or NP complete. I think it's believed that it isn't, by the way, but I'm not sure. And one of the reasons why people believe that it cannot be NP hard is because quantum computers can do factoring in polynomial time. This is the Shor algorithm, and that's kind of why everybody wants quantum computers so that they can break your security on the internet, which sounds like a great idea, but okay, not my decision. By the way, I should say that if you look at OpenSSH now have other encryption schemes that don't use RSA, that use elliptic function and so on, which are believed to be much safer. But anyway, okay. So how do you find how do you find large prime numbers? So we need two facts. Fact one is that a random number with so maybe I should not write it like that. Let me try again. There are okay. So if you choose a random number between 1 and n, roughly you have probability of 1 over log n for the number to be prime number. And the reason is because between 1 and n, there are n over log n prime numbers. It's kind of amazing. This fact is amazing because essentially almost all claim on prime numbers are hard to prove or very hard to prove. This one is not too difficult. This one could be, there is an elementary proof, that takes maybe 1 page, right? You essentially look on the right binomial coefficient and use some calculation and you get it. You need to know what you're doing, but there is an elementary, not too difficult proof. With hints, one can do it. So we know exactly how many prime numbers there are. right? Which is kind of amazing, right? Because essentially the Riemann hypothesis is related to the distribution of primes, for example. And Riemann hypothesis is considered to be like the largest open problem in mathematics. Anyway, so this implies that if you pick a random number between 1 and n, the probability its prime is 1 over log n. To remind you, log n is the number of digits you need to write a number between 1 and n, right? You need log n bits or log n digits. So essentially it says that if you pick a random number with 1,000 digits, the probability prime is 1 over 1,000. That's pretty good, right? Because you can just pick a random number, check if it's prime. If it is, great, you found a big random prime number. If it's not, you repeat. So you have to run the algorithm 1,000 times in expectation. Well, not a big deal, right? Now, of course, the question is, how do you test primality? So testing primality goes back to 1977, I think, or 70 something. Let's put a paper by Rabin. Rabin provided a randomized algorithm for primality testing. So what does it mean, it's a randomized algorithm? It's you give it a number x, okay? The algorithm computes, this is a randomized algorithm. And the randomized algorithm either output prime or not. Or it says it's not prime. If it says it's not prime, it's right. Okay. So again, if it says that the number is not prime, then it's not prime. On the other hand, if it says that it's prime, there's probability of half of it being wrong. Okay, probability half. Okay, so this is a bit bizarre, right? So you take your number, you run this Rabin test. The Rabin test, the number is prime. Well, it might not be prime, it might be composite, but the probability for that is half, right? That the algorithm made a mistake. So you run it again, right? You run it 2 times. It twice tells you that it's prime. Well, the probability that it was wrong in both execution is a quarter, right? So if the number has t digits, let's say t digits in base 2, just to make things interesting, then run the primality testing. Something like, 10t times. Right? Run it again and again and again. Every time you run the randomized algorithm, you're using different randomization. If in any of the execution, the algorithm returns that the number is not prime, it's not prime, because when it says it's not prime, it's always right. Now, if in all the execution it says that it's prime, then the probability that it fails is something like 1 over 2 to the 10t, right? And if you think about this probability is extremely small, right? It's, to begin with, the number has t digits, so the number is at most 2 to the t, right? So the product of those two things is extremely, essentially the probability that the algorithm was wrong on all the execution is extremely small, and as such, you run it. You're looking for a prime of 10, let's say 1,000 bits. You run the algorithm 10,000 times the probability the algorithm was wrong in all those execution is so small that you can just say, who cares? We can just decide, and the probability that the algorithm is wrong is much smaller than 1 over the number of atoms in the universe, etc. We can just say this number is prime and move on, because the probability of failure is minuscule. Okay, the Rabin algorithm is not very complicated. It does some bizarre calculation, modulo numbers, and understanding why it works. You need to do some number theory. So I never taught the algorithm with the analysis, because the analysis is just, you essentially have to spend 2 or 3 lectures. If you want to do everything in detail, you have to spend like 2 lectures on number theory, which is not especially interesting. But from randomized point of view, this is the interesting bit. I should mention, by the way, that roughly 10 years ago, maybe a bit more by now, people came up with a deterministic algorithm to decide if a number is prime, but the algorithm is much slower. So it's not that interesting. Now, if I remember correctly, Rabin's algorithm ran in time log cube n. Right? So if you're trying the number n, it takes something like the number of bits cubed. So it's a polynomial time algorithm in the input side, which is what we need. And that kind of was the first randomized algorithm that kind of started the whole field of randomized algorithms. So that's very cool. Okay. Question on this? Okay, so if there are no questions, I think we are done for today. I think there are other examples, but that's all I have to cover today. Let me mention one thing in the last 2 minutes, which is, of course, okay, the randomized algorithm has to make random decisions. How do you make random decisions, right? It's not like the algorithm is going to take a coin and start flipping it. So how do you do it? So in the good old days, which were not very good, you could buy random bits, literally. You could pay somebody and you will get a CD full of random bits on it. And essentially what you do, how do you get random stuff? You check some random physical phenomena, right? So think about some source of radiation, and you count the number of practicals that you get in a second, and this has some certain distribution. And if it's above if it's above a certain value, you output 1. If it's below a certain value, you output 0, and you just repeat it, right? So that was the good old days. Nowadays, all the modern CPU has an assembly command that essentially returns you a random bit using essentially some physical process in the CPU, right? So it supposedly should be totally random. If you don't believe that this randomness is totally random, right? You believe in conspiracy theory or whatever, you just don't trust the manufacturing, right? Intel has a history, both Intel and AMD, for example, have history of making major bugs in their design. So they might think it's random and might just not be random because of some default in the design. Then you have to do something else. Linux, for example, has a system command to get random bits, and it uses the user input for randomness. So every time you type a keyboard or move the mouse, whatever, it uses it to fill up its random pool, and then whenever you ask for a random number, it takes number from this random pool. And then, of course, it also uses this other sources of randomness to get to mangle the values. Linux, in fact, have two kinds of random calls to get random numbers. Some of them are blocking, right? So if the pool is empty, it would ask you to move the mouse or type something on the keyboard before it would return your random number, which is a bit bizarre, but it kind of makes sense. But anyway, for our purposes, getting a random bit or getting a random number is a constant time assembly command, and it can be done, so we don't have to worry about it. Okay, this is it for today. Thank you very much. I'm going to stay around for a few more minutes if there are questions, but otherwise you can sign off. Thank you.
Is there a book that could help us?
Yes, there are many books. You don't have to buy any of the books. So I think there is info. I didn't post it to the webpage yet. I would update it, but the classic text is by Mutwani and Raghavan. Mutwani and Raghavan. It's a very nice book. It's by now starting to be a bit dated. And it's a very, you can buy it on the internet for free, because all books can be bought on the internet for free. So that book is a good textbook. And my class notes kind of follow Mutwani and Raghavan, not everywhere, but most of the time. And there is another good book, which I would have to link for it. I don't remember it. It's a more recent text. Yeah, and I would just put it on the webpage. Both books, somehow I don't like any of the books. I don't like the books because if you want to buy them for real, they're expensive and they don't quite cover what they want. And my class notes have typos. They're not perfect, but I think they are decent. So I think they are, as far as quality, they're not up to a textbook quality, but they're definitely good enough to use, and they cover everything that they cover in class. So, and of course, there are a lot of other resources on the web and so on, so you can always search. So yeah, but as I said, I'm not, for this course, I don't recommend it.
Thanks.
Other questions?
So I had one administrative question. So, in the homework submissions, are you usually like hard deadline kind of thing, or is there some relaxation for late submissions kind of thing, a possibility as well, or?
It's a graduate class. I'm not going to provide solutions to the homework, so so.
No, I meant like. I am expecting in my one of the weeks I'll probably be caught up in something, and I'm just hoping.
Deadlines are not holy. Let's put it this way, right? So if you're late, you're late. Right? This is not, yeah, deadline. Within the limits of common sense and reason, the deadlines are it's one of those things. You should stand with the deadline. If one or twice during the semester you ask for a few more days, I'm not going to throw a fuss.
Okay, thank you.
So deadlines are not holy, but they should not also be ignored, because if you start ignoring them, then why have them? Yeah. Other questions? As far as the homework, since I'm going to grade them, you would have to submit them in LaTeX. But as I said, you would be allowed or even required to do them in groups. So hopefully, and there would not be too many homeworks. So hopefully it would be a reasonable load. Any other questions? Okay, so in that case, let me check the chat. Is there anything in the chat? Oh, what are some interesting open problems? I don't think I didn't speak about anything, well, except for the, yeah, I don't think I spoke about everything that there's a natural open problem. Usually if something comes up, I mention it. In generally speaking, the biggest open problem is that the belief is that randomization doesn't buy you anything, right? So the belief is that any randomized polynomial time algorithm, there should be an equivalent deterministic algorithm. Namely, the belief is that randomization, at least complexity-wise, doesn't buy you anything. And this is, of course, widely open. But, you know, in practice, it's not relevant at some level, right? Because from theory point of view, whether you have a linear time algorithm or cubic time algorithm, it's equivalent. In practice, if you have a randomized algorithm that runs in linear time instead of cubic, you know, it's a huge difference. And that's what happened with randomized algorithms. They tend to be much faster in practice or even in theory. So kind of, yeah. And as such, by the way, for some of the problem we will see, we will know only randomized algorithms. But then the natural question is, what is the equivalent deterministic algorithm? Right. And in some cases, we believe such a deterministic algorithm should exist, but we don't know what it is. And in some cases, some of the big results over the last 20 years were some randomized algorithm that people figured out how to do them deterministically. Or even there were some existential randomized algorithm that people turned into an efficient randomized algorithm.
So like, what about like for the coin flip problem with the triangle?
Yeah.
What? So we believe that there should be a deterministic algorithm to deal with
No,
that?
it's not, because it's not an algorithm. It's a game, right? So it's not.
Oh, okay.
It's not really a standard algorithm problem, right?
Okay.
That's why you cannot really think about it as an algorithm. But I was cheating a bit. Sorry.
Okay, I see. Thank you.
Okay.
So is
Other questions?
yeah, sorry, I don't know them.
Oh, I can't hear you. If there's anybody asking questions, you should probably increase your volume. Any questions? Or we are done?
I think they're typing it up in the chat or something.
Oh, okay. Let me check the chat then. Because the chat window disappeared again. Okay.
Test.
Is it believed also for approximation? No, I don't think so, right? So there are randomized algorithms where it's known that there is no deterministic algorithms. The famous example is volume estimation of polytopes, where it's believed that we know how to approximate it in randomized time, but no deterministic algorithm can exist. So yeah.
Sorry, just to clarify something simple, I guess. So these sort of interactive games, those aren't. Is it not possible to state them into like an algorithm problem, or is it? Or
no, you're really into game. You're starting to be about game theory, right? Because,
okay.
You know, algorithms. The way we usually think about algorithms is that there is an input, the algorithm runs. There is an output, the game is over. Right. This is it. Right. But when you speak about games, you have a multi-round, right? Things go back and forth. So it's really a different model, right? So usually when I speak about algorithm, it's only one round.
Right, okay.
So And that's, that's one of the reasons why people care about game theories, of course, because when you speak about computers, you're not really, most of the time we don't have algorithms, right? You have some system that runs on and on and on and perform a task repeatedly on and on and on. And then you have the setting of a game, really. You're doing some task repeatedly.
Right.
And so, yeah.
So is there like any, or is this like is there any, I understand that there are different models, but are there any classes of problems that can be translated back and forth, or is that like a thing, or?
So that's a good question. There is the connection, let's put it this way, right? So some game theory problems can be solved by coming up with algorithms, right? And sometimes when we speak about randomized algorithm, you're going to use some game theory procedure, but I don't think the link is like, there's no, it really is a separate field. Maybe that's the right way of saying.
Okay.